The morning of October 15, 1943, arrived cold and grey at Aberdeen Proving Ground in Maryland. Captain James Morrison pushed through the fog, hanging low across the facility's testing grounds, his breath visible in the crisp air as he made his way toward the maintenance bays. What waited for him inside Building 17 would challenge everything he thought he understood about military engineering. The captured Japanese vehicle sat in Bay 3, and Morrison stopped dead when he first saw it. The Kurogane Type 95 looked like someone had taken a real military truck and shrunk it down to a toy, complete with bicycle-sized wheels that barely reached his chest. 14-inch wheels, a compact body that would have struggled to measure halfway up his 6-foot frame. And underneath all that cramped metal, a motorcycle engine, just a motorcycle engine, producing a mere 33 horsepower. Morrison's team at Aberdeen had spent the past 2 years tearing apart German panzers and Italian tankettes, studying their innovations and precision manufacturing. They'd examined the massive Panzer IV tanks that dwarfed American Shermans. But this little Japanese scout car was something entirely different. Standing next to their American Willys Jeep with its 60-horsepower engine and 3,000-pound frame, the Type 95 looked almost comical. Everything Morrison knew about American military doctrine said the same thing. More power meant better performance. Bigger engines, heavier frames. Maximum capability across every mission profile. The American approach had always been straightforward. If commanders needed something done, American industry would build it bigger, stronger, and faster than anyone else. But then Morrison read the maintenance logs. 18,000 miles of continuous operation through Philippine jungles. 18 months of non-stop service with nothing but basic field repairs keeping the thing running. When his mechanics fired up that tiny engine for the first time, it purred as smoothly as something fresh off an assembly line. The sound didn't match what Morrison was seeing. This vehicle should have been dead, stripped of functionality, worn out, falling apart after that kind of punishment. Instead, it ran like it had barely been used. Morrison realized he was looking at more than just inferior engineering, struggling to keep pace with American superiority. He was looking at something that challenged every fundamental assumption his team operated under. These Japanese designers hadn't been trying to build a better Jeep. They'd been solving an entirely different problem. The intelligence cable had arrived 3 days earlier from the Pacific Theater, marked as priority technical analysis required. What made it unusual wasn't the vehicle itself. Aberdeen had seen plenty of captured enemy equipment roll through its gates since Pearl Harbor. Twisted remains of Italian tankettes, battle-scarred German half-tracks, even intact panzers that had taught American engineers more about armor design in 6 months than the previous decade of development had revealed. But the field reports accompanying this particular shipment were different. American forces in New Guinea kept finding these small Japanese scout cars abandoned in perfect working condition, not just functional but maintained with meticulous care. The maintenance logs showed service records that defied everything Morrison understood about reliability under combat conditions. It didn't make sense. Nothing about this made sense. Morrison walked deeper into the workshop. The high bay area buzzed with activity even at this early hour. Sergeant Robert Chen, one of the Army's finest automotive specialists, was already hunched over a German transmission, his experienced hands feeling for bearing wear patterns that might reveal metallurgical weaknesses. Nearby, Technical Sergeant William Macready stood before a workbench covered with captured Japanese small arms. Macready's deeply weathered face bore the unmistakable sun-darkened tan that only came from 18 months in the Pacific, and his presence always brought a certain weight to any technical discussion, the weight of someone who'd actually kept American equipment running in conditions that would have made most men quit. "That Japanese vehicle arrived yesterday," Chen called out without looking up from his work, his voice carrying the skepticism that had become his trademark when dealing with captured enemy hardware. After 2 years of analyzing German equipment that consistently impressed with its precision and innovation, Chen had developed strong opinions about what separated serious military engineering from inferior design. "Bay 3, we've got it staged and ready." Morrison walked toward the designated bay, his footsteps echoing across the cavernous concrete floor. What greeted him looked less like a military vehicle and more like someone's weekend hobby project that had somehow gotten mixed into a shipment of actual weapons. The Type 95 measured just 11 feet long and 5 feet wide, smaller than civilian automobiles he'd seen parked on Baltimore streets. Its drab paint showed the expected scratches and dings from field service, but the overall condition spoke to maintenance performed with almost obsessive precision. Most striking were those wheels, 14 inches in diameter, barely larger than motorcycle wheels, wrapped in tires so narrow that Morrison questioned how they could handle the rough terrain of military operations. "Jesus," muttered Corporal Danny Walsh, one of Morrison's junior engineers, walking a slow circle around the vehicle. "Is this thing actually supposed to be military? My kid brothers got a pedal car bigger than this." Walsh had spent the previous year analyzing massive German vehicles, and the contrast between that experience and what he was seeing now was stark enough to provoke genuine laughter. The small size simply didn't compute in the context of military equipment. Morrison climbed into the driver's seat and immediately felt uncomfortable. The interior had been designed for much smaller occupants. His frame felt cramped in a space clearly optimized for the average Japanese soldier's build. The dashboard was spartanly functional, basic gauges, simple controls, nothing requiring more than minimal mechanical training to operate. But as Morrison examined the details more closely, patterns emerged that suggested more thoughtful engineering than the vehicle's diminutive appearance implied. The gear shift pattern was unusual. Instead of the standard H pattern found in American civilian and military vehicles, the Type 95 used a sequential layout that allowed shifts without using the clutch. That kind of feature would be invaluable when climbing steep terrain with limited traction. The steering wheel itself was positioned at an angle that seemed awkward at first glance, until Morrison realized it had been deliberately designed to provide optimal control when the vehicle was tilted at extreme angles. "Let's see what kind of engine they put in this thing," Morrison called to Chen, who was already approaching with his standard toolkit. Mechanical diagnosis was Chen's specialty. He could identify problems simply by listening to an engine's characteristics, a skill that had helped American manufacturers improve their own designs. Chen released the hood latches and lifted the engine cover, then stopped completely still. "Captain," he said slowly, "you need to see this." Something in his voice caught Morrison's attention. Not skepticism, not disappointment, genuine confusion. Morrison joined him at the engine bay and found himself staring at what appeared to be a motorcycle engine adapted for automotive use. A 1,345 cubic centimeter air-cooled V-twin producing just 33 horsepower according to the identification plate, less than half what the Willys Jeep's four-cylinder delivered. But what struck Morrison most forcefully wasn't the engine's modest output. It was the obvious sophistication evident in every component. Cooling fins perfectly uniform, carburetor housing displaying machining tolerances that rivaled anything Morrison had seen from German manufacturers. This wasn't crude adaptation, this was precision. "Rikuo engine," McCready said, joining the group around the open hood. His voice carried the authority of someone who'd spent considerable time maintaining American equipment in impossible field conditions. "Japanese license-built Harley-Davidson. I've seen these before. They were using them in motorcycles and light aircraft before the war. Reliable as hell, actually." McCready's endorsement carried weight. If McCready said something worked, it worked. Morrison found himself facing a puzzle that challenged fundamental assumptions. American doctrine emphasized maximum capability. The most horsepower, the heaviest payload, the fastest speed. The Willys Jeep embodied this philosophy perfectly: 60 horsepower, 800-pound cargo capacity, maintained highway speeds. Everything designed to dominate. But here was a vehicle built according to completely different principles. And according to field reports, it was performing missions that American planners would have considered impossible for such a modest machine. The maintenance log in the glove compartment told a story that Morrison's engineering experience suggested should have been impossible. 42,000 miles through Philippine jungle conditions. Engine overhauls performed using just 16 basic tools. Months of continuous operation with nothing more than routine field maintenance. Either Japanese record-keeping was completely fraudulent, or Morrison was looking at engineering solutions his team had never considered. "Gentlemen," Morrison said quietly, straightening up and looking at his team gathered around the small Japanese vehicle, "I think we're going to learn something here." Over the next 3 days, Morrison immersed himself in intelligence files, tracing the parallel development stories that had led to these two radically different approaches to military transportation. The contrast began with the specifications themselves, documents that revealed how completely different strategic assumptions had shaped engineering priorities on opposite sides of the Pacific. The American story started in 1940 when the Army issued specifications for what would become the Willys MB. The requirements read like a commander's wish list, one drawn up by planners who assumed unlimited industrial capacity and well-developed logistics networks. The new vehicle needed to haul 800 pounds of cargo, climb 60% grades, maintain 60 miles per hour on highways, service everything from reconnaissance to light artillery traction. American engineers approached the challenge with characteristic optimism. If the Army wanted maximum capability, the automotive industry would deliver it. Willys Overland responded with a machine that embodied American automotive philosophy. The MB's 2,199 cubic centimeter inline four-cylinder engine produced 60 horsepower, enough to pull a 2-ton trailer up mountain roads or chase German reconnaissance units across North African deserts. Its 3,000-pound curb weight provided stability and durability. Its sophisticated transmission and transfer case allowed operation from desert sand to European mud. By American standards, the Jeep represented perfect balance, power, versatility, reliability all working together. But the intelligence files revealed completely different priorities driving Japanese development. In 1936, as Japanese forces became increasingly committed to the vast expanses of China, Army planners faced logistical challenges that American commanders could barely imagine. Japanese supply lines stretched thousands of miles through territory where roads existed only as optimistic lines on maps. Fuel depots were separated by weeks of travel time. Maintenance facilities consisted of whatever tools individual units could carry with them. Major Hiroshi Tanaka's captured reports provided insight that official documents couldn't convey. Tanaka had commanded reconnaissance units during the Philippine campaign, and his detailed analysis painted a picture of warfare conducted under constraints that would have paralyzed American forces. Average patrol distances of 20 to 30 miles over terrain that destroyed conventional vehicles. Fuel allocations measured in gallons per month rather than per day. Maintenance schedules built around the assumption of no access to specialized tools or replacement parts for months at a time. Out of the depths of technical specification emerged a portrait of engineering caught between two worlds. The Type 95's 33 horsepower engine sipped fuel with remarkable efficiency, consuming barely 3.6 gallons per 100 miles. Stand that against the American Jeep's thirsty appetite of 6.7 gallons over the same distance, and you're looking at machinery designed for entirely different circumstances. But efficiency wasn't the only advantage hiding in those numbers. The air-cooled engine eliminated a vulnerability that had crippled countless American vehicles. When radiators failed under combat stress, when cooling systems gave up the ghost in tropical heat, American equipment simply stopped. The Japanese machines kept running. This power plant descended from motorcycle engineering, born from decades of refining engines meant to run continuously at steady RPM. When Japanese designers adapted that heritage for automotive use, they created something that seemed to defy conventional wisdom about vehicle reliability. Chen's deep technical analysis revealed solutions that challenged everything Morrison's engineers thought they understood. The independent suspension system used torsion bars instead of leaf springs, a choice that gave superior movement over broken terrain while keeping the overall weight down where it mattered most. Those 14-inch wheels that Morrison's team initially dismissed as inadequately small actually performed brilliantly under field conditions. They distributed the vehicle's modest weight across a larger contact patch than standard military tires, resulting in ground pressure of just 8.2 pounds per square inch, compared to the Jeep's 12.1. The transmission itself represented perhaps the most remarkable achievement in Japanese automotive thinking. Rather than the complex synchronized gearbox found in American vehicles, The Type 95 employed a sequential system pulled straight from motorcycle technology. Shifts happened without touching the clutch, and the gear ratios were specifically chosen for slow-speed maneuvering through difficult terrain rather than highway cruising. The differential locked using a simple mechanical lever, providing maximum traction whenever needed without the engineering complexity of modern limited-slip designs. Macready's field reports from New Guinea supplied real-world proof of these design choices working under actual combat conditions. American forces had initially written off captured Type 95s as inferior to their own Jeeps, but extended observation revealed performance characteristics that contradicted these quick judgments. On jungle tracks that swallowed Jeeps in mud, these lighter vehicles pressed forward. During river crossings, the Type 95's sealed electrical system and waterproof engine operated in water depths that rendered American equipment useless. Most significantly, Macready recorded maintenance intervals that seemed almost impossible given the brutal operating environment. Type 95s recovered after 18 months of relentless jungle operations showed engine wear consistent with civilian vehicles under normal conditions. The air-cooled engine's service life of 6,000 hours vastly surpassed the 2,500 hours expected from water-cooled automotive engines struggling through tropical climates. Simple carburetor designs kept functioning at extreme angles that would flood conventional systems. The absence of complex emission controls or performance modifications meant that repairs could happen with basic tools far from any supply depot. The captured maintenance manual revealed its own story about Japanese engineering priorities. Engine overhauls required exactly 16 standard tools, all of which a single soldier could carry. Component tolerances were designed to accommodate field machining using portable equipment. Replacement parts stayed standardized across multiple vehicle types, reducing the logistical nightmare of maintaining mixed fleets under combat conditions. Yet Morrison's analysis uncovered the strategic constraints that had shaped every Japanese choice. Japan's entire aluminum production in 1942 totaled 18,000 tons, roughly what American aircraft manufacturers consumed every 3 weeks. Steel allocations for military vehicles competed directly against warship and aircraft production, forcing Japanese engineers to minimize material usage rather than pursue performance optimization. The Type 95's modest specifications reflected not inferior engineering capability, but the harsh mathematics of industrial capacity grinding away under wartime pressure. These implications reached far beyond individual vehicle performance to fundamental questions about military logistics and strategic planning. American forces deployed vehicles that guzzled fuel and demanded frequent maintenance because their industrial base could support such approaches. Japanese forces operating at the end of increasingly fragile supply lines needed equipment that could function independently for extended periods with minimal external support. Morrison realized he wasn't comparing superior versus inferior engineering, but two completely different solutions to fundamentally different problems. The Americans had designed a vehicle for a war they could sustain with unlimited industrial capacity. The Japanese had designed a vehicle for a war they expected to fight alone, thousands of miles from home with whatever resources they could transport. Both approaches made complete sense within their respective contexts, but those contexts differed so profoundly that direct comparison became almost meaningless. The question wasn't whether the Type 95 was better or worse than the American Jeep, but whether American planners had considered all the variables that Japanese engineers had been forced to address from the very start. Testing commenced at dawn on October 23rd, with Morrison's team preparing Aberdeen's most challenging terrain obstacles for systematic comparison between the Type 95 and a standard Willys MB. Aberdeen's engineers had constructed testing courses replicating battlefield conditions from every theatre of operations. North African sand dunes, European mud, and most relevant for this analysis, Pacific jungle terrain complete with steep grades, loose soil, and simulated river crossings. Chen positioned himself behind the Jeep's wheel for the first series of trials, while Morrison took control of the Japanese vehicle. The initial hill climb used Aberdeen's standard 60% grade obstacle, a punishing incline that had challenged every piece of American equipment during development testing. Chen engaged four-wheel drive in low range, then accelerated up the slope with characteristic American directness. The 60-horsepower engine roared, pulling the 3,000-pound vehicle up at 15 miles per hour, demonstrating the brute force performance that had made the Jeep legendary among American troops. Morrison followed in the Type 95, immediately noticing how different the Japanese approach felt from behind the wheel. The 33-horsepower engine didn't roar. It hummed with a steady, almost musical note suggesting mechanical components operating well within their design limits. The sequential transmission allowed Morrison to shift without using the clutch, maintaining constant power delivery as the vehicle climbed. But the Type 95 couldn't match the Jeep's dramatic assault on the slope. Instead, it climbed steadily at 8 miles per hour. The small engine never straining, the drivetrain never showing signs of stress. Differences became more obvious during extended testing. After 30 minutes of repeated hill climbs, the Jeep's engine temperature gauge showed readings that concerned Chen, while the Type 95's air-cooled power plant maintained consistent operating temperatures regardless of workload. Morrison understood that Japanese engineers hadn't designed their vehicle to match American performance specifications. They designed it to operate sustainably within its capabilities rather than pushing toward maximum limits. Fuel consumption testing revealed even more dramatic differences. Aberdeen's standardized 100-mile course included highway sections, off-road terrain, and stop-and-go urban simulation designed to replicate realistic military operations. The Jeep completed the course in 2 hours and 45 minutes, consuming 6.7 gallons of gasoline. Its superior power-to-weight ratio allowed aggressive acceleration and high cruising speeds that American drivers expected from military vehicles. The Type 95 required 4 hours and 15 minutes to complete the same course, but consumed only 3.6 gallons of fuel. Morrison found himself adjusting his driving style to match the vehicle's capabilities rather than fighting against them. The Japanese machine encouraged patience and mechanical sympathy rather than the aggressive operation that American equipment was designed to withstand. But the fuel economy implications staggered the imagination. Over the course of a typical month-long Pacific Theater operation, a Type 95 would consume roughly half the gasoline required by an equivalent American vehicle. McCready's participation in the testing provided crucial battlefield perspective that laboratory conditions couldn't replicate. Having maintained both American and captured Japanese equipment under combat conditions, McCready understood the practical implications of design choices that seemed theoretical to Aberdeen's engineers. He demonstrated how the Type 95's simple carburetor continued functioning when the vehicle tilted at angles that would flood conventional systems. A critical advantage when traversing steep jungle paths characterizing Pacific Theater operations. The maintenance testing produced results that challenged everything Morrison's team understood about military vehicle reliability. Aberdeen's standard maintenance protocol required 147 different specialized tools for major service on the Willys Jeep, reflecting the vehicle's sophisticated automotive engineering. Transmission overhauls required hydraulic lifts, precision measuring instruments, and component specifications demanding factory-level equipment. This complexity ensured excellent performance under normal conditions, but created significant logistical challenges when proper maintenance facilities weren't available. The Type 95's maintenance requirements told a completely different story. Major engine service could be accomplished using exactly 16 standard tools, all fitting into a canvas roll weighing less than 10 pounds. Component tolerances were designed to accommodate field machining using portable equipment, while standardized fasteners eliminated the need for specialized wrenches or sockets. McCready demonstrated a complete engine overhaul in less than 6 hours, using tools that could be carried in a standard infantry pack. Chen's detailed analysis of both vehicles after 500 hours of testing revealed wear patterns that surprised Aberdeen's engineers. The Jeep showed mechanical stress typical of high-performance automotive equipment, transmission synchros worn from aggressive shifting, engine bearings stressed by high RPM operation, suspension components fatigued by repeated impacts. These wear patterns were normal and expected for American military vehicles, designed to deliver maximum performance during their service life, then be replaced when maintenance costs exceeded operational value. The Type 95 displayed completely different wear characteristics. After 500 hours of operation that would have stressed American equipment to its limits, the Japanese vehicle showed minimal component wear. The air-cooled engine's internal parts measured within factory specifications. Transmission components showed no significant degradation. Most remarkably, the independent suspension continued functioning smoothly despite repeated impacts that had damaged Jeep leaf springs during parallel testing. Morrison began understanding that Japanese engineers had optimized for completely different performance criteria. Where American designers maximized short-term capability, Japanese engineers prioritized long-term sustainability. The Type 95 wasn't designed to match American performance specifications. It was designed to continue operating when American equipment had been destroyed or abandoned due to maintenance difficulties. Intelligence reports from ongoing Pacific operations provided real-world validation of Aberdeen's testing results. American forces advancing through the Solomon Islands were finding abandoned Type 95s in various states of maintenance, many showing service records documenting continuous operation for 18 to 24 months with only field maintenance. Captured maintenance logs indicated that some vehicles had operated for over 40,000 miles in jungle conditions that would have disabled American equipment within months. But the same reports revealed the Type 95's strategic limitations. As American forces gained momentum during 1944's island-hopping campaign, Japanese vehicles couldn't keep pace with mechanized advances. The Type 95's modest power output prevented it from hauling the heavy equipment needed for large-scale military operations. Its limited payload capacity meant multiple vehicles were required for missions that a single Jeep could handle. Morrison realized the profound implications of his team's analysis. The Type 95 hadn't failed because it was poorly engineered. It had succeeded brilliantly within its design parameters, then been overwhelmed by operational requirements exceeding those parameters. American industrial capacity allowed the luxury of over-engineering equipment for maximum capability, while Japanese constraints forced innovative solutions that optimized different performance criteria entirely. The question wasn't whether American or Japanese engineering was superior, but whether each approach was appropriately matched to the strategic context in which it operated. Morrison's investigation expanded beyond individual vehicle performance as intelligence reports from across the Pacific painted a picture of two fundamentally different approaches to industrial warfare. The strategic analysis files crossing his desk in early 1944 revealed resource constraints shaping Japanese engineering decisions in ways American planners were only beginning to understand. The numbers staggered in their implications. Japan's entire 1942 aluminum production totaled 18,000 tons, roughly equivalent to what American aircraft manufacturers alone consumed every 21 days. While American engineers could specify aluminum components whenever weight savings justified the cost, Japanese designers faced brutal choices between aircraft production and lightweight vehicle components. The Type 95's extensive use of steel rather than aluminum reflected not technological backwardness, but ruthless prioritization of limited strategic materials. Steel allocation presented similar constraints that American engineers had never faced. Intelligence estimates suggested Japanese military vehicle production competed directly with warship construction and aircraft manufacturing for identical raw materials. Every pound of steel used in a Type 95 represented steel that couldn't be used for aircraft engines or naval armor. This context explained design choices initially puzzling Morrison's team. The vehicle's minimal weight reflected not just performance optimization, but fundamental resource scarcity, demanding maximum efficiency from every material input. McCready's detailed reports from Pacific theater operations provided ground truth validation of how these constraints played out in actual combat. Average Japanese island garrisons numbered 8,000 to 12,000 troops supplied by transport ships arriving every 45 to 60 days, when Allied interdiction allowed any supply runs at all. Under these conditions, equipment requiring frequent maintenance or consuming excessive fuel became operational liabilities rather than force multipliers. The maintenance records painted a stark picture that American logistics experts were only starting to grasp. The Type 95 maintained an operational availability rate of roughly 78% after half a year in the Pacific Theater. Compare that to American Jeeps laboring under identical conditions. They achieved just 34% availability. The gap was shocking, but the reason wasn't what most assumed. It wasn't about superior Japanese manufacturing prowess. Rather, it revealed two fundamentally different philosophies about keeping equipment functioning in harsh, isolated conditions. Morrison dug into captured maintenance logs from Guadalcanal, studying the Japanese engineering mindset as recorded in meticulous detail. Individual Type 95s had run continuously for more than 12 months, maintained exclusively through field repairs performed by ordinary infantry troops armed with basic hand tools. Engine rebuilds happened in jungle clearings using equipment lightweight enough for 2 soldiers to carry. Parts replacement followed systematic procedures requiring nothing beyond elementary mechanical knowledge. The strategic implications crystallized as Morrison set these Japanese standards against American maintenance expectations. American Jeep upkeep demanded specialized tools, trained mechanics, and constant access to replacement components manufactured to exacting tolerances. That worked beautifully when American forces held secure supply lines and had established repair facilities nearby. But once units found themselves isolated or cut off from regular logistics support, the system collapsed. Incoming intelligence from 1944 operations illustrated how sharply these divergent maintenance philosophies shaped battlefield mobility. American mechanized columns could push forward swiftly and deliver overwhelming firepower when their supply lines held firm. Yet this capability rested on enormous logistical infrastructure. Japanese forces advanced slower, but their equipment kept running in zones where American machinery simply seized up due to lack of support. The Type 95's fuel appetite became particularly revealing when examined through the Pacific Theater's logistics lens. American vehicles guzzled roughly 4 gallons daily during standard operations, a consumption rate demanding continuous fuel deliveries by ship and extensive fuel depots on captured islands. Japanese vehicles averaged less than 2 gallons daily, slashing logistics demands by better than half. Morrison grasped this wasn't merely about engine efficiency. This represented an entirely distinct vision of mechanized combat. American doctrine rested on logistics dominance, designing equipment for maximum immediate power without worrying about supply chain constraints. Japanese doctrine accepted logistics vulnerability, building equipment that could sustain operations independently with minimal outside assistance. The industrial files revealed how thoroughly these philosophical divides ran through both nations' factories. American automakers, Willis, Ford, General Motors, had converted civilian assembly plants to military specifications, bringing generations of high-volume production expertise to military vehicles. Their output reflected civilian automotive values, comfort, performance, and planned obsolescence, encouraging steady replacement cycles. Japanese producers like Kurogane drew from motorcycle and aircraft engine foundations, adapting proven designs rather than starting fresh. This heritage gave their vehicles the durability and service characteristics of aviation equipment, systems built to perform reliably across thousands of hours with sparse maintenance. The manufacturing philosophies diverged sharply too. American production prioritized interchangeable parts made to tight tolerances, enabling speedy assembly and straightforward replacement, yet demanding precise quality control and expensive specialized machinery. Japanese production accepted looser tolerances and engineered components, allowing field adjustment, reducing factory complexity while raising maintainability in austere settings. Morrison's researchers uncovered something remarkable. Japanese engineers had thoroughly studied American automotive methods, then deliberately chosen different paths based on their strategic realities. Recovered technical papers showed extensive analysis of Ford and General Motors operations, followed by deliberate decisions emphasizing different qualities. These designers weren't attempting to replicate American vehicles. They were solving an entirely separate problem. The strategic picture emerging from Morrison's investigation showed two warring nations fighting with completely opposite assumptions about manufacturing capacity and logistics capabilities. American hardware optimized for brief, intense campaigns, supported by limitless industrial output and sophisticated delivery systems. Japanese hardware optimized for extended campaigns in remote locations where replacement was impossible and maintenance help was scarce. As 1944's island-hopping dispatches accumulated on Morrison's desk, the strategic reality sharpened. American factories churned out military machines faster than they could be deployed, permitting replacement of damaged or worn equipment with newer models. Japanese factories struggled to replace losses, squeezing extended life from existing vehicles. The Type 95's construction made perfect sense within this framework. Japanese designers had created a vehicle persisting when fresh machines were unobtainable, needing minimal resources and minimal logistics support. American designers had built a vehicle maximizing immediate output, knowing industrial capacity would handle whatever maintenance and replacement challenges appeared. Morrison began organizing his preliminary conclusions. Understanding his team's findings reached implications far beyond simple vehicle performance. The Japanese hadn't engineered inferior machines. They'd engineered precisely what their strategic circumstances demanded. American advantage lay not in superior design thinking, but in having the industrial muscle to select engineering approaches Japanese constraints wouldn't allow. The real question wasn't whether one engineering philosophy surpassed another, but which suited its strategic environment better. Morrison sat in his Aberdeen office on a frigid March morning in 1944, surrounded by 2 years of test results, combat reports, and technical studies fundamentally reshaping his comprehension of military engineering. The documents piled on his desk constituted the most thorough examination of foreign vehicles American forces had conducted, though his conclusions troubled him by contradicting established beliefs. Daily intelligence arriving from Pacific operations recounted accelerating American advances, yet they also exposed weaknesses that had ultimately sealed Japanese equipment's fate despite its engineering quality. Macready's latest communication from Guadalcanal depicted abandoned Type 95s littering the landscape, not because they'd failed mechanically, but because their operators had been engulfed by America's sheer mechanized onslaught. Vehicles succeeding brilliantly in extended jungle campaigns couldn't match the velocity of American offensives. Morrison's concluding performance review showed how the strategic terrain had transformed since 1942. American forces now swept forward with such material preponderance that Japanese fuel economy and repair advantages seemed irrelevant. When American logistics delivered boundless fuel and spare components to recently conquered islands within weeks, the Type 95's careful design for resource limitation lost strategic worth. Yet Morrison recognized this didn't diminish Japanese engineering accomplishment. It merely demonstrated how superior design could get swept aside by strategic forces beyond engineers' control. The Type 95 had functioned precisely as intended, performing brilliantly under the constraints shaping its creation before collapsing when those constraints vanished. Chen's comprehensive technical study undergirded Morrison's most consequential findings. Following 18 months of rigorous testing, the Type 95 had shown mechanical toughness exceeding American equipment under particular circumstances. Its air-cooled engine displayed virtually no deterioration after operating intervals that would have taxed water-cooled automotive power plants beyond acceptable limits. Independent suspension persisted smoothly after collisions destroying conventional leaf spring assemblies. Most strikingly, uncomplicated maintenance had permitted repairs using tools and methods American mechanics could readily manage. These technical discoveries were already reshaping American military vehicle design in transformative ways. Morrison's suggestions had reached Army development divisions, where specialists were incorporating Type 95 features into future equipment. Independent suspension, derived from Japanese innovations, appeared in preliminary American test vehicles. Streamlined maintenance practices entered specifications for machines destined for international deployment. Influence extended beyond immediate military needs to fundamental engineering questions, defining American automotive development generations forward. Morrison's research demonstrated peak performance didn't necessarily mean optimal performance. Constructing machines to function sustainably within specific limits could yield better extended outcomes than systems chasing maximum capability. Morrison retrieved the maintenance records, launching his investigation 2 years back, documents still astounding him with their significance. 4,200 miles through jungle terrain using only field maintenance. Engine rebuilds accomplished with 16 simple tools. Component changes performed by infantrymen needing minimal preparation. These accomplishments represented engineering solutions American creators were scarcely comprehending, much less replicating. The strategic picture Morrison's investigation revealed challenged American presuppositions regarding industrial warfare. Vast manufacturing capacity didn't invariably yield superior equipment. It simply permitted different engineering strategies. Japanese limitations had pushed creative answers American abundance never demanded, producing capabilities American engineers were now struggling to copy despite dramatically superior assets. Morrison's ultimate report would chronicle how the Type 95's seeming shortcomings proved actually advantageous, perfectly calibrated for Japanese operational needs. Modest horsepower prevented the damage-prone failures plaguing higher-powered machines. Skinny tires distributed mass efficiently across marshy ground. Its straightforward fuel system continued operating through angles that would choke complex carburetors. Each limitation served strategic advantage within its operational context. Survival numbers conveyed the complete narrative of technological brilliance ultimately crushed by strategic circumstance. Of approximately 4,034 Type 95s manufactured throughout hostilities, merely 23% remained serviceable by war's termination. Not from mechanical collapse, but from strategic collapse, leaving even perfectly good machines scattered across conquered islands. Equipment engineered for independent prolonged function met a conflict forbidding such independence. Morrison grasped the vital understanding buried in these figures. Engineering achievement transcended mere technical performance metrics, requiring consideration of strategic conditions and operational environments extending beyond individual hardware specifications. The Type 95 prospered as an engineering accomplishment, while disappointing as a strategic instrument, showing how technical excellence could become meaningless when battlefield circumstances shifted. Post-war American engineering already showed Morrison's influence through continuing consultation with Detroit automotive companies. Ford's research team examined Japanese upkeep methods for incorporating into civilian machines destined for foreign distribution. General Motors investigated independent suspension for prospective military applications. Chrysler evaluated air-cooled technology for specific purposes where water cooling created exposure. Morrison prepared his final conclusions with deliberate consideration toward their broader significance. The Type 95 symbolized perhaps the finest example of resource-limited engineering applied to wartime transport. Its seeming drawbacks were genuinely strengths matching intended purposes. American predominance stemmed not from superior ingenuity, but from resources allowing engineering possibilities Japanese circumstances prevented. Future military vehicle creation would incorporate design approaches prioritizing serviceability and resource conservation alongside traditional power metrics established through Morrison's documentation. He'd shown that occasionally superior engineering emphasized matching capability to resources rather than maximizing power alone. As Morrison finalized his formal assessment on March 15, 1944, he contemplated the essential truth his years of investigation had revealed. Those Japanese engineers hadn't designed an inferior American Jeep. They'd designed exactly what their war needed. That this vehicle couldn't deliver victory reflected strategy and manufacturing might, not engineering capability. Ultimately, greater manufacturing resources could surpass superior engineering, though this didn't erase the technical triumphs resource constraints had necessitated. The Type 95 imparted a critical lesson. Invention frequently sprang from restriction, and the most sophisticated answers typically surfaced from embracing limitations rather than overwhelming them through superior power.